Okay, good afternoon, everybody. Welcome to Friday. You've officially completed 1 week. Take the little wins. Okay, so as we mentioned last time, Monday is going to be office hours in 2:15. That's the drop-in time. Again, we've got the room booked at that time. If it doesn't meet your time, please do email me. We'll figure out some other time to meet up. There is a Piazza poll currently running on Piazza to figure out when to better sort of align that time. Any update on that point? When it closes today, I think, right? Okay, so second poll running, yes. If you've already voted once and you voted for a Friday option, please do go back and add your next choice from that particular part. All right. So from last class, we had a very quick catch up on Chem 123 and 203. Remember, these are things like bond order, hybridization, what pi bonds are, how antibody orbitals work. And we started talking through the carbonyl group. So remember, the carbonyl group is our kind of core piece. This is how we get our aldehydes and ketones. What makes an aldehyde and ketone special compared to an amide, an ester, or carboxylic acid? If you had to divide those two, what's the special part? Yeah?
There's resonance for an ester and an amide.
Yeah?
But there's no resonance for ketone.
Yeah, exactly. So all of these compounds, esters, aldehydes, carbonyl, they're all carbonyl compounds that have this core sort of carbon double bonded oxygen. Ketones and aldehydes have only carbon-hydrogen over at these two positions. They're only stabilized by hyperconjugation. That's how we help with the deficit of charge at that reactive center. Anything else where there's a heteroatom with lone pairs over here, like an ester, those lone pairs can participate in resonance, which adds extra stability to the carbonyl. The reactivity changes. They are less reactive in general than ketones or aldehydes. So that's why we split them out, is because there's reactions that only work with that sort of center. We started talking nucleophilic additions and cyanohydrin formation. Cyanohydrin formation is the first example of a nucleophile that's not super awesome. You need to activate the carbonyl to get the addition to happen. So we've had these two kind of parallels, which mirrors what you've seen with something like an SN1 reaction. If an SN1 reaction has a okay nucleophile and a really good leaving group, that reaction can happen, carbocation formation can happen directly. If you had a poor leaving group like a hydroxide, you need to undergo an activation step with a bronzed acid, then the nucleophilic addition. That's the analogy from SN1. For cyanohydrin formation, similar balance. Carbonyl on its own is not good enough to be attacked only by CN-. You need to protonate the carbonyl first, increase the electrophilicity, now the addition can happen. So we're starting to mix things like acid-base chemistry with nucleophilic additions and reversibility. So, as we did last time, first round, take about a minute, think this one through, try to do this one yourself. Think about what you think the major organic product of this reaction is going to be. Take about a minute and do this one in your head, then we're going to work out the conversation. Okay, turn to the person next to you. What is your answer? What is their answer? How did you come to that answer? That's the important thing to sort of debate as you talk about this. Okay. And time. Okay, all together in one big creepy voice. The answer is C. That's right. And again, you can do this partly by process of elimination. If you take the materials that you're putting into this reaction, why can I eliminate E? What bonds are you breaking to make E? How do you go from that chunk of starting material over to E? What would you have to do? Yeah, you're fracturing the ring. You're taking what would be a carbonyl into an alcohol. There's a lot of stuff going on there. If you actually count protons, hydrogen stuff, this does not match. You're missing atoms to make this thing work. Something like A looks close, except if you're doing this addition, all you're doing is an addition between fragments. You're adding this CN group, or one of these CN groups, to this center, and the hydrogen ends up on that oxygen. You're just recasting or reforming this sort of center. The important thing to look at this, too, is that is now the carbonyl, but it's masked. As C, this is our cyanohydrin. That's the reaction that we talked about last time with these conditions, right? Buffered sodium cyanide HCN. This guy here is an addition reaction where that's kind of still, it's got the spirit of a carbonyl. You just made this new carbon bond formation, but it's got this double addition to that center. You've converted it completely back to sigma bonds. All right. So today we're going to start talking about carbonyl activation again. More on this whole point of starting to make reactions happen that don't necessarily want to happen initially. And we're starting talking about different functional groups or conversions into hemiacetals, hemiketals, acetals, and ketals. These are our new players in this case. So we talked about this briefly last time. Remember, carbonyls on their own have a delta positive center down here. This center is our delta plus. The oxygen is their delta minus. That's the normal polarization that happens giving the carbon that electrophilic character. And that polarization means it's reactive to nucleophiles at this center. However, again, if we really want to help out a poorer nucleophile, we can actually increase the overall dipole here by making this center even more positive by basically putting a formal charge right next to it. By protonating that oxygen, taking advantage of that delta negative charge, I can protonate it and then give it even more of a dipole. That increases the overall activity of this. So why is it more reactive in acid? We've basically stretched out or otherwise removed any stabilization that might happen by having that lone pair nearby. I'm actually pulling away even more charge from that center and making it even more carbocation-like. So these are our new groups, what we call the hydrate, acetal, ketal, hemiacetal, hemiketal. And everybody immediately panics of, oh my God, I now need to know 5 brand new molecules. This is the point where, again, most of organic chemistry are derivatives of similar concepts. So play the game, Sesame Street. What looks similar, what looks different as you go left and right? So can you group these things together? What's kind of close to each other? Yeah, so first off, acetal versus hemiacetal. What's similar about those two compared to ketal, hemiketal?
For your acetal and your hemiacetal, you keep your R prime and H, but then your hemiacetal, you keep half of the ROs to OH.
Yeah, there you go. Ketals and hemiketals come from ketones. They come from carbons on both sides. Acetals and hemiacetals come from aldehydes. So these guys, both of those derive from R carbonyl hydrogen. The ketal, hemiketal derives from R carbonyl R prime. So they're only different by manipulations at the carbonyl center, but their fundamental base is similar in that case. So instead of being 4, there's really these 2 that come from the 2 ones we've been talking through, acetal and ketal, or acetone, aldehyde and ketone. Okay, hemi, what does hemi mean? Half, yeah. And if you look at this, right, the addition of 2 R groups, that gives it the full name of acetal-ketal. If I only have one of the R groups and the other chunk is my OH, that's my hemiacetal or hemiketal. So whether or not you have 2 of these alcohols added to the center versus only 1, that's how you split these 2. Hydrate, what does hydrate look like? So if I was to, again, we're going to go through the mechanism in a second, but I'm kind of saying that to go from, let's say, a ketone to the aldehyde, to the hemiacetal, I'm really adding this alcohol group. Here I'm adding OH and H. What is H, O, and H? What molecule is that? Water, H2O, and that's why we call it hydrate. You're taking a carbonyl compound, and specifically this is a hydrate of what? What was the hydrate if I just rip water out of it? What does it become? That becomes a aldehyde or a ketone. Ketone, because I have R and R prime. This was just a ketone that we picked up water with. So all of these guys, even though they look different, first thing to start practicing through here is what makes them common derivatives. Do not panic. These are not 5 different things. It's really one common principle where you're changing. How many nucleophiles do I add? 1 or 2? What is the nucleophile? Water or an alcohol? And what was my base? An aldehyde or a ketone, right? It's those 3 permutations that you're working through. Okay. We're going to work it up in different steps. First, it happens in the sequence. The acetal or ketal turns into the hemiacetal hemiketal, which then turns into the acetal, the final compound. So we go to the hemi first, and then we go to the full compound. It happens in 2 different stages. Mechanisms are very similar for both of the 2. How this works out is we can use a trace acid or base to add to my carbonyl compound, where I'm specifically here, I'm kind of grouping them together. This includes the aldehyde and the ketone in this general structure. And if I'm adding an alcohol, remember, if I just swap that to a hydrogen, that's water. That's why this is really the same thing, right? Water is just wet alcohol, right? It's just an alcohol on its own where you're just swapping out that last R group. If you look at this, left to right, which side of the equilibrium do you think is favored? From what you know about these kinds of molecules, the relative stability, do you think this is a product-favored reaction or starter material-favored reaction? Louder? Why? More stable, yeah, but why? What gives it the stability?
You would say that, for example, hemiketal and hemiacetal, they're more stable when they're in a cyclic formation.
Okay, yes, more stable and cyclic. That's a specific example, but what is it bonding? What is the bonding, or what gives it that energy balance that says those should be more stable? What do you have on this side in terms of the bonds which are different? Yes?
The CO double bond is more stable.
The pi bond is a really good thing. If I've got a pi bond, I can hold on to a pi bond. I'm basically compacting that energy into that center. Versus here, I've got 2 electronegative atoms, 2 oxygens, pulling on one center, sigma bonds only. There's sterics that crowd onto it. There's a lot of ways that I can easily get over that barrier to snap back into a nice, stable pi bond. Sterics may hurt me a little bit to try and go over there. There's too much stuff crowded around one center. There's a couple of reasons, but the basic energetic principle here is if I have only one equivalent of this or one equivalent of this in a catalyst, these are catalysts that we're using here, catalysts will typically make the reactions faster. It doesn't change where the balance is, but energetics says carbonyls are going to win, carbon double bond oxygen. Now yes, if we have cycles, there's some specific cases where we can favor it the other way by the structure. But if this is an acyclic molecule, you're really going to favor the carbonyls, which just means hemiacetals and ketals, they're really, really hard to isolate. The hydrate forms, not easy to isolate at all. They can form in a reaction. They can exist as part of your mechanism, but you're not going to put them in a flask and hold on to them. They will fall apart back to their constituent components very easily. So how do I actually get this reaction to go? If I want to make my hemiacetal or ketal, what can I do to make that happen? The Chatelier, right? The answer is not catalyst, right? If I add more acid, I just speed up the equilibrium. I do not change the delta G between those 2 centers. If I need to push it to the product, I need to have a lot more of a starting material, or I need to remove a product from this reaction. Same thing, if I want to go the other way, I need a lot less of a starting material on this side, and I can drive the reaction. So these chemistries, what we're talking about in this part of the section, these are not kinetically driven reactions. They do not form faster. This is all about Le Chatelier to push and pull on an equilibrium. So you're either adding excess of one starting material or you're withdrawing a product in order to drive it the way you want. Okay, so how does this part work? The mechanism of the trace acid one, we're going to break it up into 2 steps. If I'm going to run this reaction with a trace acid catalyst, the first thing I'm going to do is add a strong acid, let's say. Now what we're going to do is draw this out where I'm adding a strong acid to a system, in this case my alcohol, and because I'm trying to drive it towards products, typically what I'm going to do is run this reaction with excess alcohol. That becomes my solvent a lot of the times. If I'm going to drive this reaction fully forward, I will have my solvent be my alcohol, which means the first step in this equilibrium is usually a strong acid like HCl will hand off that proton to somebody else. Usually if we're drawing this out in terms of just, again, we're trying to show you sort of best practices. First step, the alcohol will pick up the proton to give me my protonated alcohol species. Remember, this comes back to the principle we've said about something like HCl. It loves to ionize, doesn't really want to hold on to that proton. You've got anything else for it to hand that proton to. In this case, if it's the solvent, it passes it to the solvent. This is the same thing we guys saw in SN1 type chemistries. Right? So this is what you can say is kind of your precursor. This is getting ready for the reaction. It's just putting a steady state of where that proton is going to sit. All right. Now that we have our carbonyl compound, so that's our aldehyde or our ketone, and we've got our proton source. This is the proton holding on to the alcohol. What I have to do, remember, is I'm trying to put these 2 pieces together. I have excess alcohol here. I've got my nucleophile. So you can imagine floating around in solution, there might be more alcohol sitting around. But like we talked about with the cyanide, this does not happen initially. Just because I have a ketone or an aldehyde and an alcohol, they're not going to undergo a nucleophilic addition first. You can draw this out where if I take a neutral ketone and a neutral alcohol, alcohol is not nucleophilic enough to hit just that carbonyl yet. This is where we have to activate it first, just like we did with the cyanide.
What if it's not stop at the Hemi score and just promote it like
If you have enough and enough time, yes, absolutely. So when we jump it through, but it goes stepwise. We're going to take it piece by piece and show we can form here. If you're fast enough, if you control how much of the alcohol it is, you can stop on that, but it's kind of like running on ice. Absolutely. It does become a trick, and we'll show you in the base case that is how we can stop. So we'll show you that part next. But first thing I want to emphasize is do not do that neutral addition. This is where we have to activate the carbonyl first. We've added the acid. The first step is going to be carry out an acid-base reaction to form our activated carbonyl compound. Okay. Now, just for mass balance, and again, I'm not showing the chloride here anymore. We got rid of it just for brevity, but remember, by mass balance, there's still a chloride here in the solution nearby to sort of balance out the charge. We've handed the proton back to the carbonyl. It's activated enough now. Now, we're going to do the addition. This addition step, if you remember back from first class, this looks like, or second class, excuse me, this looks like our cyanohydrin addition. The nucleophile is adding to an activated carbonyl. So you go from a positively charged intermediate to a different positively charged intermediate because I have this neutral species here. This is going to be an equilibrium again, which I'm going to get my alcohol bit and R prime and O R R. Am I done? Is that correct? What's wrong? Where? On the O. With the R. Right here, right? The nucleophile was neutral. You're adding to a positively charged species. Make sure your charge balances. Yeah?
Just a quick question. On exams or when we do work, are we expected to write down like the chlorine ion throughout this entire process?
Up to you. Good practice. Think of it where, again, English doesn't have the nice sort of, formal versus colloquial versus, street, let's say. If it's quicker for you to go through this point, this is completely correct. Dropping that chloride and then drawing your mechanism where you're moving it, not a problem. Just because sometimes those counterions are massive, tosylate, whatever, it can be a big part. If you want to keep it in there, it's not wrong. If for brevity on this, your diagram, it makes it easier for your intermediates not to show it, that's fine. Read the question is the best example I can say, right? If I'm asking you something where I need you to pay attention to that ion, I will specify it in the question itself. But this kind of like colloquialism to delete it temporarily for the mechanism is totally fine. The other big question I usually get too is, well, you just took the proton HCl, you gave it to the alcohol, and then you gave it from the alcohol over to the carbonyl. Can't I just take HCl and give it to the carbonyl first? What do you guys think? Who says, no, that doesn't make sense? Who says, yes, you probably can? You're both right. Honestly, what I care about is you guys do not add neutral alcohol to neutral carbonyl. No bueno. You must activate your carbonyl first. If you prefer to activate your carbonyl directly from HCl, that is not wrong. It's just rare. What I mean by that is usually if you do this reaction, you're going to have the carbonyl, a catalytic amount of acid, and a whole buttload of alcohol. Probability says the proton's going to find the alcohol first. So all we're representing here is the general sort of, call this like the best bookkeeping mechanism. I'm going to show you sort of the best practice. But if you choose to just do the protonation first from the acid, that's not wrong. You won't be marked against it. I'm just giving you sort of best practice. Okay? Yes?
On the exam, did you used to show the electron on the oxygen?
Oh, lone pairs? No. Like, again, welcome to, again, you guys are adults now. The best example I can say is this. If you need those lone pairs to be clear about what you mean, you can include them. If I asked you a question about what a Lewis dot structure is, I should be shot. We're not doing that game anymore, right? I try to hold on to the point where your goal is not to ask a question that is that pedantic, right? Like right now, the lone pairs are useful to show sort of that for bookkeeping and accounting, but if you abstract them, I know what you mean, right? Any other questions? Okay. So now we're here. Are we done? No. Remember, this is a catalytic process, which means you're boring a proton and you have to get rid of it after. I'm not done yet. This mechanism is going to take another molecule of alcohol, the solvent, and I'm going to transfer that last proton, one more acid-base step, to give me my final product. So that's my R, my OH, my R prime, and my OR. That's my hemiacetal or hemiketal, where the final proton is now back to OR here. This guy here, is the catalytic species that completes your cycle. That's why we transfer it to the proton first, is because now you have good bookkeeping showing this catalytic cycle, right? And yes, there'll be a chloride chilling around for stuff. Make sense? That's the acid one. The most important is, if you have acids as your catalyst, what is the general charge of all your intermediates? Positive. Why? Because protons are positive. If you have an acid species, you're adding protons, you're adding positive charge, and all your intermediates in your cycle are positively charged, right? So you can know that's a really key thing to kind of pay attention to based on the overall charge balance of the system. So in the end, here's your good copy. Each mechanism I provide to you, I'm going to do it out in class like this. We're going to walk through it. I want you guys to have pen and paper practice. It's a good thing to kind of work through this with me, but I will always give you the good copy that does not look like chicken scratch for you guys to look through at the end. Yes?
Would this go all the way into like the full acetal, or would it stop at
That's time. If we keep pushing on it, it will. And if I have alcohol, too much alcohol, yes, it will rip through it. We're going to do that one next. I want to do the base catalyzed one first, but yes, that can happen. It's just a matter of, that's like stopping on ice, right? Depends how steep the hill is and how fast you're going. Anything else? Yeah.
Terminology.
Yeah.
When you say trace acid and trace base on the slide, are we talking about trace amount of the acid, or is that a designation?
No, trace is amount. What I'm saying, if I say trace, I mean catalytic, not stoichiometric. You do not have enough protons to completely swamp all the molecules of whatever the other species is. It's a catalyst, is what we mean. Anything else? Good question, guys. I got to say, based on every other 213 class, you guys are way more communicative. This is going to be a fun term. Giggle, giggle, smirk. Okay, let's do base. Bases are negative, right? You've lost a proton, meaning you leave behind a negative charge. If I have a trace base in the system, catalytic base, mechanism is different. We're dealing with negatively charged species now. So now, if I have a negatively charged species, let's say I've got hydroxide as my base. We're going to follow the same sort of logic we did before. The catalytic base I start off with, my strong base, hydroxide, is going to kick things off by ripping off a proton from my solvent, my alcohol. That makes this guy RO minus and water, right? What's the name of that? That is it's not an alcohol, it's an alkoxide. That's like sodium butoxide, T-butoxide, right? It's a negatively charged oxygen species that's not water. It's not hydroxide, it's an alk oxide because of this species, right? Okay. Now that I've got my negatively charged species, my negatively charged alkoxide, this is what? A nucleophile or an electrophile? My alkoxide is a nucleophile. It's a base also, but it's a nucleophile. Yes?
Why is the reactant favored? It says the reactant's favored.
Good question. What do you think?
I was thinking the product would be favored because there's more alcohol present, so it's pushed to the right.
No, remember, okay, what we're showing, you're right, that's a good question, good point. If we have it by concentration, yeah, that's probably the better way to draw it, is the product is favored by Le Chatelier. What I'm trying to emphasize here with that equilibrium is the energetics. So what I mean here is, let's just go back to that top species there. Does everybody remember the pKa of an alcohol? pKa of an alcohol is 16. What's the pKa of water? 14. Why? Because the pH scale goes from 0 to 14. So which is a better acid, water or alcohol? So if alcohol is a stronger acid, water is a stronger acid, alcohols are a better base, it's going to go that way energetically. The pKa of water versus an alcohol will typically favor the hydroxide, right? That's all. But you're right. If I did this by Le Chatelier, dumping in way more in the little, then yes, it's going to be product favored. That's how we make the reaction work. But this here is really to reflect the pKa's of the system. That's all. Okay. Now that I've got my nucleophile and my nucleophiles in the system, this is not like the first case. I'm not taking neutral oxygen, neutral alcohol, and adding to my carbonyl. I have a negatively charged system. Because it's negative, that's a better nucleophile. So I can go directly without activating. I don't have to activate this system, right? It's just like adding my Grignard reagent, for example. So now I'm going to have my carbonyl compound, R prime, R double prime, and my alcohol. So I start with an alkoxide, and I make an alkoxide, right? I've pushed up negative charge into the oxygen. And that's why I'm giving this balance that it's basically O minus and O minus. It's a wash between the energetics of the system. Okay, are we done? No, there's still a charge we have to deal with. We need to regenerate our catalytic system, our catalytic base. Yeah. Okay. So if we're going to go through and regenerate it, this is where I need to go around another cycle. Remember, you're still going to be in your alcohol solvent, so that final proton is going to be the regeneration of your final molecule. That RO8, RO minus, that alkoxide, is what we're going to start the next cycle with. So this is, again, a hemiacetal or hemiketal as we go through this species. Yes?
So if we go over why we do not need to activate.
Why do we not need to activate? Good question. So remember, we need to activate if the nucleophile is not very strong. Negatively charged species are better nucleophiles than neutral species, right? If I have a negative nucleophile, my electrophile is good enough. If I have neutral, not good enough, I need to activate it with a positive charge. Here's another one too. What if I wanted to try and do both? I want a negative OH, and I want to activate my carbonyl. Why not? That sounds great, right? If one's good, two's got to be better, right? Acid base happens first. If you try to say, I'm going to use trace base to deprotonate my oxygen, but then I'm also going to use trace acid to protonate my carbonyl, the acid base find each other and say, bye. It's just an acid. Like, remember, protons are small little species. Acid-base reactions are some of the fastest ones we have. Those are always going to beat carbon-carbon, carbon-oxygen bond formations. So you can't, that's why we have these two extremes. Under slightly basic conditions, anionic systems win, neutral nucleophiles are, or negative nucleophiles are being used. Under acidic conditions, we protonate the carbonyl first, then we do the addition. You can't fuse both the two together. Protons are just going to find, positives are going to find negatives. You'll just protonate the system. So that's your overall system here. We start off with a simple base, potentially hydroxide. We make it alkoxide, nucleophilic addition, proton transfer gives us a catalytic species here. This is catalytic in our base, which then recycles the whole process again. Now, back to the question. Oh, yeah, sorry.
Would the extra lone pair on the second to last step be favorable for the center carbon?
Sorry, guide me here. The extra electrons where?
In the second to last step.
Here or here?
No, on the negative charge.
Here?
Yeah. Would that be because it has an extra lone pair? Wouldn't it stabilize the delta positive on the center carbon?
Oh, this delta positive right here in this center? Yeah, it does. But remember, delta positive is not positive. It's just polarized, right? I have a negative charge, though. That's a full-on negative. Is it, what you're kind of ranking there is saying, what is more stable, an apple or an orange, right? All we have here is I have two oxygens attached to a center point. Yes, I have a negative charge, which kind of helps out the positive, but it's also like having two magnets pulling against each other. Both carbon-oxygen bonds are dipoles that you're actually hauling energy density away from it. That's why the thing would prefer to fall apart and go back to your carbon double-bonded oxygen. In the end, if you've got a way of satisfying this charge by giving it back a proton, you're going to do that to get to a neutral species, at least. That's going to be lower on the energy surface. Make sense? Okay. So we've got two different ways now that we've made our hemiacetal hemiketal. That's halfway through it. And we had some really good questions about, well, wait a minute, why doesn't it just move through both? We're going to get to that one in just a second. But in terms of a couple pieces here, this is just housekeeping in terms of the energetics of the system and their shapes. We start off with sp2 centers, carbonyls, right? They're sp2 hybridized. And then we're expanding them to an sp3. It goes from a carbonyl, which is this flat planar system, and it's going to expand into a tetrahedron. We're going to all sigma bonds as we do this one. So overall, as we do this addition, you remember you're going to be increasing this hybridization. You're going from this geometry part. So this geometric relationship matters because what happens to things like chiral centers? If I start with a carbonyl that's flat and I add a group to it, and those groups are not the same. So here, let's look back to this center here. That molecule, is this a chiral center? Yes or no? You've gone from an achiral molecule to a chiral molecule. And this is where we start playing things like diastereomers, enantiomers, right? We're just like we did with any addition to like a carbocation, which was flat, we're going up to something where stereochemistry and geometry matter. Those are going to impact things like relative stability of these centers. So it's one part that we have to kind of keep track of as we go through. This is why, again, the relationship with the possible products is something you have to pay attention to. If the molecule was completely achiral and you only add one new center, your two products have to be what? Enantiomers or diastereomers? If I start with something that had no chiral centers and I add one RS center, those two products have to be what? They have to be enantiomers. They're mirror images. If you've got chiral centers in the molecule and you add equal mixture of some RS, so I've got an R somewhere in the molecule and I made a new center that's both R and S, two products are now diastereomers. Again, if this is sweeping off cobwebs part, this is kind of what I mentioned before, people that are like, what do I need to review? If this is the scary review thing, let me know. I will point you to the 123 lectures where we talk through these relationship parts. But this is something you guys should be familiar with. So I want you to do the mechanisms of these, showing me all the possible products that you could make from these particular points. This is one of the practice try it later ones. I will not go through this part in class. I will do this longhand by a pen cast, and I want you guys to check it up after. I'll post at the end of the lecture. Yes? Yes? They don't work? Does anybody else run into that? Yeah, no problem. Okay, so what I will do, again, this is why I went away from Canvas. I have all the videos. I'm going to repost them on the YouTube channel, and I'll create a new link from it. So, but please, if anybody else flags that where there's problems where accessing some of the content is an issue, do let me know. So, okay, I'll take that as a note, and we'll get it uploaded. Thanks. So we mentioned this part before. In general, carbonyls are going to win. If I take two molecules, an aldehyde and a ketone that are separate molecules, generally, the hemiacetal, the hemiketal, is not your favorite species. Even if you can form it, it will much happier fall apart. It's weird because all we have to do is deprotonate it to actually spit out the two fragments and regenerate my bond. Remember, everything I showed you in the mechanism, walking forward, is the exact same mechanism, just going back the other direction. The only case where you have to pay attention, wherein the opposite is true, are these cyclic compounds. These are molecules where both the carbonyl and the alcohol are part of the same backbone. You guys remember this from probably 203, 233? We have these general rules where like everything is fine until one of two things happens. Everything is fine until resonance or aromaticity. That's one thing that screws up everything. Or everything is fine until rings. Cyclic rings are stable because of geometry, because of orbital overlap. This changes the game slightly. And there's two rules I want you to remember here. If you can form a 5-membered ring or a 6-membered ring from a molecule, that will happen. That is possible. That's number one. Now, what do you think is more reactive, aldehyde or a ketone? What did we say before? Just think of just that functional group. Aldehyde versus a ketone. Which do you think is less stable, or which do you think is more reactive? Aldehyde. Why? Hyperconjugation not enough, right? So aldehydes are more reactive than ketones. That's saying that if I have an aldehyde and a product, aldehyde is less stable than the ketone. I'm talking about the stability of my starting material, right? So look at the first example. 90% of that first one will exist as a 5-membered ring. The second one is a 6-membered ring, but it's only 50%. Why is that cool? What's going on there? They are both, over here, everybody agree, these are both hemi what? This is a hemi acetal, this is a hemi ketal. Remember back to first, second year? What is more stable in terms of your ring size? 5-membered rings or 6-membered rings? 6 is awesome, right? You have no sort of ring strain. You've got those perfect bond overlaps for sp3 centers. The 6-membered ring here is actually not as stable as the 5 because this is a ketal. So what we're trying to do is show you two different phenomenons here. Reactivity, acetals win over ketones. That's number one. In general, 6 will win over 5. So if I had something like, bloop, a 6-membered acetal, that's awesome, versus a 5-membered acetal. But a 6-membered ketal versus a 5-membered acetal, the thing I'm trying to emphasize here is still acetals win over ketals, generally. So this is where we're showing you nuance, where reactivity is one part of the diagram, and then relative stability is the second part, 6 versus 5 ring. We're starting to mix different pieces. So again, I want you to go through this part here, draw out the mechanisms, and again, this is where you should know, and this should feel good about, okay, why is this 50% relative to the cyclic form? Why is this 90% relative to the acyclic form? We'll do that part after. So for anybody who's done biochemistry, do you recognize these structures? Did anybody have some type of sugar or beverage or food today? Yeah, that was not enough hands. These are your carbohydrates. These are your sugars. This is the energy content for how we store a lot of quick energy, right? We take carbon compounds and we store it as things like carbohydrates because breaking them down and burning them releases a lot of energy too. This is how we turn these into CO2 as part of our primary glycolysis kind of systems. The interesting thing about these is these guys are hemiacetals, hemiketals. If you notice, this is the open chain form of my aldehyde and an alcohol, and this is the closed form. This is the hemiacetal form of things like glucose. So your sugars are typically these hexopyranoses or hexofuranoses, number of carbons in that structure, and they almost always exist in these kind of closed structures, right? So again, this is what goes back to depending on what type of sugar you have, that's where you have either an aldehyde or a ketone in the background, and then what ring size it forms depends on different parts of the body. This is where usually the 6-membered rings are going to be favored over the 5s. So again, we want you to go through and practice this. Draw this molecule, and more importantly, now we've got a chiral center. This is where I've got a carbonyl and already a chiral center into it. You're making a pair of diastereomers here, depending on which face you may actually form. There's geometry optimization, geometry problems that start to come into this as well, because the face of this carbonyl you may approach, either from the top or from the bottom, will enforce different geometries of your ring. Okay, so I'll do this part after for you guys to watch at the end of the video. Okay, so that's hemiacetal, hemiketal. But if we want to go all the way to acetals or ketals, the good news is you can only use acidic systems. Basic conditions will always stop at the hemiacetal or hemiketal. Acidic systems, you can go through the hemiacetal or hemiketal form to your product. So you can use this to your advantage. If you want to set up a reaction where you want to try and freeze out that intermediate, you can use a basic system to stop at the hemiacetal or hemiketal. Acid is one where you have everything you need to move forward. And we'll look at it in the mechanism. This should pop out at you of why this is possible. So all we're doing here is if I add 2 equivalents of an alcohol under acidic conditions, I get my acetal. 2 equivalents of that same alcohol, acid conditions, I can make my ketal. So I'm just doing 2 iterations of what I've shown you before. So we'll start off with that first half of the mechanism. This is the same mechanism we described. Under acidic conditions, you're going to start by activating your carbonyl. So we get the thing ready. We do our nucleophilic addition of our alcohol to the activated carbonyl. We have a positively charged intermediate where we hand off that last proton to get us our hemiacetal or hemiketal. And we still have our catalytic acid regenerated. That's the first part we saw through. Now we're going to do that second addition. This is where it's slightly different. Remember, look at your mechanism. The way we do this first addition of alcohol is I take a proton, I activate my carbonyl, and then I do a nucleophilic addition. I no longer have a carbonyl. My product here, I don't have this simple carbonyl structure, but I do have lone pairs. And if you look at sort of the inventory of what we're trying to do, to go from my hemiacetal or ketal, all I have to do is get rid of that. That OH has got to go away. And I've got to replace it with an alcohol, ROH. Now think back. What is another reaction you guys have had where you're trying to get rid of an OH and replace it with another nucleophile? Make it to a leaving group. Yeah, sorry. SN1, right? I can take an alcohol. If I protonate that alcohol, I can lose it like water via carbocation, right? So this is where all I have to do is get rid of, jettison this water one. So we start at that hemiacetal or ketal. I still have my acid. Instead of, if I did this, I'm going to protonate my oxygen. Just for a second, what would happen mechanistically if I did this instead? What if I do dark green versus light green? What am I doing with dark green? I'm going backwards. That's not wrong. Dark green is not wrong. It's just not productive. You're going to walk your way back to your carbonyl. That's how you break down hemiacetals. That's the penultimate step from our last piece. So it's not that it does not happen. It's just not productive for the reaction we're trying to do. So we do the light green structure first. Now I do this addition. I'm going to get my OH H plus. I've primed it to be a leaving group. So this is similar to what you do for an SN1 reaction. Okay, so if this was SN1, what do I do? Somebody give me a bond geometry. Where do I start with my electrons? What am I trying to pull off? That OH2 is your leaving group, right? So I could do this. If I just jettison that part, I'm going to lose water, neutral. What do I leave behind if I do that? If I kick out neutral water, I leave behind carbocation, right? So I'm going to draw that just in this step. So let me just do this part first. If I did this, okay, you can look at it as it's still in equilibrium. And it's going to be R double prime, R prime, O, R. And there's a positive charge on this carbon, right? Okay, it's a carbocation, but this is a special carbocation. This is not your average carbocation. This is actually more stable than a normal carbocation. Why? What's that? Resonance, one bond resonance. On its own, a normal carbocation only has hyperconjugation to help it out. But just like the esters or the amides, I have right next door lone pairs. So I can also draw this as a resonance structure Is that right? What are you missing? Where? There you go. If you move the bond down, it's not a carbon plus, it's an oxygen plus. Again, this is an oxyanion. It's not super, super happy. It's still better than nothing, right? You've still got a little bit of help. It's still better than normal carbocation. Which of these is correct? It's resonance, man. They're both there, right? Don't be a dumb organic chemist here. These are not separable molecules. These are resonance structures of the same molecule. These are different representations or Lewis structures. So now we've got this intermediate. I've activated the center. I just have to bring my other oxygen in. I have to bring my other alcohol to the party. So my other alcohol here is going to be this system. I'm going to take this lone pair, and we're going to add to that center. It's going to be my OR, and I brought in OHR positive over here now. Yes? Oh, sorry. That's just Jason's lazy. Yoop. There you go. That's a fat iPad arrow. That's all. Yes, goes to the oxygen. We're not done yet. Last step. I need to transfer this proton. Again, this is where you have to regenerate your catalyst. Your catalyst was this species here. So you're going to have another molecule of your alcohol. We can pick off that last proton, and we get our final compound. This is where we have our now full acetal. And I want to draw this out with different colors. The first alcohol that went in was that blue one. The second one is here. What's the other product of this overall step? We've also got our catalytic acid, right? But there's one more thing I want to make sure I write down as a product here. What else was ejected from this whole system? Water. The final product as we go through this is also one molecule of water. And that is critical. Because remember, Le Chatelier, you've got two things you can do to help you out. Lots of a starting material, lots of alcohol will help push you through to a product. I can also dry the reaction. If I can sequester that oxygen, that water, I can push the reaction forward. Okay, guys, have a great weekend. I will see you on Monday. Okay, what's up, guys? We're going to go through some of these practice problems. I hope you've tried them out, and I'm going to go through the solutions. So in this case, this is our first one. Just for note, we're going to be using an addition of a aldehyde, alcohol, and trace acid. Because of the first part of our lecture, you may recognize this as the addition of into this carbonyl with this nucleophile. Trace acid is going to be our catalyst, and it's going to give us a hemiacetal or hemiketal, at least initially. We're only going to take it as far as that hemiacetal. I know at the end of the reaction we start talking about the addition of two equivalents of this, but let's just do the first addition initially. So if we're going to do this addition, the way this mechanism might work, I'm going to have my proton source. I'm going to just draw that associated, and because we're under acidic conditions, we're going to protonate that part first. So we've now activated our carbonyl, and now we can bring in our oxygen nucleophile, which is going to give us our first addition product. So if we've protonated it, that's now going to be neutral on that center. And now, this is a first reminder, we discussed this very briefly. The carbonyl, when we start out, is an sp2 center. It's flat. When we do this addition, we're going to be increasing the hybridization from sp2 into an sp3 center. Because this is a flat center, and you can see that there's a carbon, oxygen, and a hydrogen, this addition of this other alcohol is actually going to generate a chiral center at this point. So I'm going to show this where there's possibly one of two different addition geometries. One from the top face. So if we were to add, let's say this alcohol here comes in from the top, that means I'm going to draw this out of the plane of the page as a wedge. OH, and our ethyl, that's going to contain our positive charge, where then that will push that hydrogen to the back. Now we can have the same molecule, same addition, but let's say we're going to do it from the bottom. So same arrows really, but it's just the other product you would generate from there is going to give you your alcohol, and I'm going to just draw that explicitly where now dash is going to be our OH plus, and that pushes the hydrogen from the aldehyde up like this. Now these are not the final product. In both cases we can draw them as separate steps. There's going to be something that has to deprotonate, or a final step in this case might be another molecule of our alcohol acting as the sort of final proton transfer, picking off this proton. In the other one, same kind of thing. I'll just give it a different color. That alcohol would pick off this center to do the acid-base reaction here. The two final products you get after sort of this equilibrium, we're going to have two molecules as our hemiacetals in this case here, and I'll just keep the color coding the same. So going up is our O ethyl, and down hydrogen, and over here we've got our alcohol, and down O ethyl, and wedge is hydrogen. So if you look at these two molecules, the relative relationship of these two, we have a single center that can be given that RS notation. There's 4 different groups with different CIP priorities. These two molecules are enantiomers of each other. Okay, so we're going to erase this to do the bottom half of this problem. So very similar. We're going to do an addition again under trace acid. So we have our proton. Once again, we will activate my carbonyl, and that's going to give me the cyclohexanone. So this is my activated ketone now, positively charged. And as before, now that this is positively charged, we can bring in my nucleophile. So nucleophile can attack into the center and then punch up. Now the difference, unlike the first case, here this is a symmetric molecule, right? Both sides, these two carbons have the same CIP priority. There's a plane of symmetry down the middle of the molecule. So that just means it doesn't matter if I add to the top or bottom. You can draw these out to prove them to yourself. But in fact, this addition will give you the same molecule regardless of the addition to the top or bottom face. It's just that we're adding and we're not generating a chiral center. So it would be appropriate just to draw this either achiral or just a single geometry. So I'm going to draw one with the oxygen back and then the nucleophile that came in, which is this propyl group, positively charged, like that. So then the final step is to take our alcohol, which will be our proton carrier. It's going to add, over here is the equilibrium to give you your final product as your hemiketal in this case. And again, there's only a single geometry of this present. So for this next problem, in the previous slide, we were talking about the formation of the cyclized forms. So we're just completing the equilibria of what these might look like if a molecule that contains both the oxygen alcohol, the nucleophile, and the electrophile carbonyl in the same molecule. So if you look at this one, on top we have a structure that we've got both those two centers, and this is 1, 2, 3, 4, 5 atoms away. So that's going to give us our nucleophile oxygen, and that center are going to attach. We're going to get a new carbon-oxygen bond. So under trace acid conditions, we're expecting to see a 5-membered ring form. And that means, actually here, let me get the color coding to match. So we have a 5-membered ring forming based on the numbering we did before. Oxygen number 1, 2, 3, 4, making this carbon number 5. And if you look over here, carbon number 5 is going to have our other oxygen, this other carbonyl center. So that will, once this is all done and proton transfer is finished, it'll be an O like this, and we still have a methyl group attached. So the last group would be a methyl. So this here is our hemiketal, or a cyclic hemiketal structure, because we're starting from a ketone. To be more explicit, I'm actually going to redraw that center showing stereochemistry. So I'm going to draw, let's say, the methyl back and the oxygen forward. And you would also have potentially the other enantiomer where the other geometry is also present. In the bottom case, we have our already cyclic form. So this 1, 2, 3, 4, 5, and this time oxygen is number 6. We're going to be breaking the bond right here. It's going to be the bond between the nucleophilic oxygen center, seen there, and this carbon number 1. So it's going to be a scission of this carbon-oxygen bond right here. So that'll give me a linear form. So that's where I'm going to draw this out, where I'm going to have my OH. Remember, it's a 6-membered ring, so oxygen is 1, 2, 3, 4, 5, and 6. That will be my carbonyl. So again, adding my numbers into this, if I had oxygen is number 6, I can go with 6, 5, 4, 3, 2, and then carbon number 1. So look back here, carbon number 1 is a hemiacetal, which means the only other atom I'm missing to draw in is a hydrogen. So that would be the form that we have over here. As we mentioned before, generally 6-membered rings win over 5-membered rings, but in addition, acetals, or cyclic hemiacetals, are much more stable, favored relative to cyclic hemiketals. Here this would be a 50-50 mixture of both the cyclic form and the other, because we have both a hemiketal but also a 5-membered ring, which contrasts what we had over here, where we have a 6-membered hemiketal, which is again in that sort of middle kind of range. The 5-membered ring over here is really reflecting the stability of the hemiacetal form, rather than just being a 5 versus a 6-membered ring selectivity. Okay, so in this case, we're just going to do the addition. The addition could happen under either trace acid or trace base or catalytic acid base condition. When we do this, we're focusing on the intramolecular reaction. That's just because, again, we've got 1, 2, 3, 4, 5 atoms that can potentially form this ring, including the nucleophilic oxygen, electrophilic carbonyl. So that's the first step. We are identifying that a intramolecular reaction is possible, and more importantly, it is a 5-membered intramolecular reaction involving those atoms seen here. The one other part to bring to the party, though, is we have a asymmetric center right here. That carbonyl is going to be attacked in this way, and there's both attack from the top face or from the bottom face. Well, actually drawn better would be sort of think from the top, where this would have an approach as a corresponding wedge, or sort of from the back underneath that center here. So we're going to represent both of those two. The best way to do this, like what I like to do first of all, is go through and number off the atoms. So 1, 2, 3, 4, and 5. Those are the ones that are involved in the ring itself. So I'm going to redraw this as a 5-membered ring here. And again, giving it the numbering that corresponds to my starting material. I'm calling this oxygen 1, carbon 2, 3, 4, and carbon 5. Now carbon 5, you notice, has this R group attached to it, and we'll have this oxygen. This is the center that can have some variability if it's going to be attacked via the top or bottom center. So I'm going to draw one geometry where the oxygen, what used to be the carbonyl, is now OH, and then out of the page is my R group, like this. So that's oxygen number 1 there. We're not finished yet. If you notice, we still have the group attached to carbon number 2. So carbon number 2 here has this 3-carbon unit attached to it, and the geometry of that center will not change. Carbon 2 here, remember, you're only doing a nucleophilic attack of this oxygen, which means this stereochemistry is being preserved. Whatever you had in the starting material must be reflected in the product. There's nothing about this reaction which is changing that stereocenter. So in this case, I would draw this as up, and then my propyl group. So let me quickly redraw that. So it's going to have the geometry like this, and then other 2. So that's my 1, 2, 3 center attached into it. Now, if you ever need to check yourself, basically what we're saying is, if this center here was R, it will still be R. Or if this center here was S, it's still going to be S. There's nothing that's changing the overall assignment or geography of that center. So labeling it, carbon number 1 here has the highest priority, oxygen has the highest priority. We're left with 2 possible carbons, and if you count these out, this center here will actually be number 2. This is 3. The missing center, number 4, is my my hydrogen to the back. So in a similar way, that is shown here, 1, 2, 3, lowest to the back. This is my R center. It's the clockwise rotation as we go through that CIP. So in this case, we have oxygen is number 1. This carbon center here, again, the one that's attaching out to the carbonyl, the extended center over there, it's going to be higher priority. That's number 2. This is 3, and once again to the back, not shown, is the hydrogen, which is my number 4. So again, once again, this is 1, 2, and 3. Same geometry. This is an R center. So I'm just doing the CIP as a final check. Again, you can do this by your molecular model kit, or again, manipulating it in your mind. So that's one of the 2 possible products we can have here. Remember, we're mentioning that they're going to be a pair of diastereomers because this stereocenter is not being manipulated. This stereocenter can have either the top or bottom face. So this center here has one more possible geometry. So I'm going to redraw a 5-membered ring. Once again, this is oxygen number 1, 2, 3, 4, and 5, where the attack geometry would be from the opposite face, giving me OH and R like this. However, carbon 2 will have exactly the same geometry. You're not manipulating it, so whatever you have for one possible product, you'll have the same for the other. That's just coming along for the ride in this edition. And that's why these two are diastereomers to each other, because the stereocenter is the same, this stereocenter is different.